That's right. So thanks, Yao. It's great to be back at CU. I'm having a great time living in the dorms. It's a lot of fun. We had a lot of new people, and looking forward to tonight's beer pong tournament, for example. Wait, am I being filmed right now? So that was just a joke, of course. So the title of my talk has changed a little bit, but the content's pretty much the same. We're going to talk about synthesis. Do I need this?
Yeah. Yes.
Right? Okay.
It's hard to hear back.
Usually this is not a problem. We're going to talk about synthesis and assembly of colloidal quantum dots, and then kind of unscheduled is a lot more on charge transport properties of these materials. So the outline is going to look like something like this. First, a little intro to semiconductor quantum dots. We'll talk about what they are and why we care about them. The methods that we use to actually synthesize quantum dots, at least the most typical kinds. And then a lot about fabrication and characterization of quantum dot films. So these are conductive films that are pure quantum dots with no other phases present. Probably tomorrow morning, in my second talk tomorrow, we'll get into the details of charge transporting these materials, and then apply those principles and lessons to quantum dot solar cells to understand the state-of-the-art and the existing challenges. Okay, so the first thing today is mostly a primer on quantum dots. We're talking about colloidal semiconductor quantum dots. So these are materials that we make in solution, chemically made. So they're a little bit different than the epi-grown quantum dots that were described in the previous talk. They are, of course, nanometer-sized crystals that have size-dependent properties. So that's one of the definitions of a quantum dot. And we can make them using fairly straightforward techniques that are pretty well refined at this point into lots of different kinds of materials, so especially clusters or spheroidal kinds of quantum dots out of 4-6 compounds or 2-6 compounds or 3-5s. We can control shape a little bit, so we can make cubes, for example, or elongated structures, things that are like rods. Even though I'm cheating here, those are actually metal nanorods, not semiconductors. And more advanced structures, things like tetrapods, where we have a central core and we grow arms out of material. So this is quite common for structures that can adopt both the zinc blende and the wurtzite structure. You can go kind of a step beyond in terms of the sophistication of the syntheses into things like looking at core shell quantum dots, which is an example of a core shell quantum dot shown here. So this is lead selenide on the inside and cadmium selenide on the outside, prepared by ion exchange. There are also more axial kinds of quantum dots that might be better for solar applications. Core shell quantum dots, of course, especially if you can find one of the carriers in the core, is not going to be such a great material for a solar cell application. One of the nice things about these structures is since they're made in solution, we can use self-assembly to make thin films from them. And I showed two examples of kind of a partial monolayer or bilayer of quantum dots on a surface of silicon in this case, and then a self-assembled superlattice structure that's also made by just spin casting that we'll talk about a little later down the road. Okay, so quantum dot physics. Basically, when you have a semiconductor that has a dimension, the question? Yeah. Sure. So my definition for nanocrystal is a crystal that's got one dimension or more that's less than 100 nanometers in size. Quantum dots are those that actually have quantum confinement properties. So the quantum dots will be a subset of nanocrystals. Okay. So when you have a semiconductor that has a dimension, one or more dimensions, that's on the order or smaller than the natural size of an exciton or the size of an electron or hole, then we say that that particular particle or material is quantum confined. And we appeal to things like particle-in-a-box type physics to understand what's going on. Basically, as you have a very, very quantum confined particle, your electronic spectra evolves from kind of bulk bands to a set of discrete states. And the discrete states, the energy dependence, or the energy between them depends on the size of the object. So we can understand this basically by looking at kind of simple models from quantum mechanics, including the infinite quantum well here, just a one-dimensional particle in a box of side L. And we know, of course, that the energy levels there are going to be inversely proportional to the square of the length of that box. Now, in a quantum dot, we have a three-dimensional particle in a box, or really a particle in a sphere, but the general principles are the same. and overall the energy level dependence is basically the same. It turns out not to be usually L squared, but something like L to the 1.5 power, something like this. But the bottom line is that when we have quantum dots, we have a density of states that's discrete and atomic-like. Okay, so we have, usually for say lead selenide, we would have a HOMO level and a LUMO level separated by the band gap. And the HOMO level we would call the 1sh, the 1s level for the holes. The LUMO level we would call the 1se, the 1s level for the electrons. And they have topologies that are very similar to normal atom states. So we call these artificial atoms or superatoms. Okay, of course the quantum dot, three-dimensionally confined, is just one member of the family of dimensionally confined semiconductors. And this slide here shows kind of the evolution going from bulk material that's three-dimensional to two-dimensional material, one-dimensional material, and then to quantum dots. So we have 1 degree of quantum confinement here and 2 directions for the quantum wire, and then all 3 directions for the quantum dot. In this table, the table shows the wave function and the energy spectrum for each of the individual types of objects, as well as the density of states. So we can see, for example, that the wave function for a bulk semiconductor is basically a product of 3 traveling waves, right? Complex exponentials, in just a sec. And so what this means is that if you have traveling waves in all directions, then your energy is going to be the energy of a free electron. This is in the free electron approximation. So as you confine dimensionally, we confine in one dimension, we turn one of the directions, in this case x, from a traveling wave into a standing wave. And so we have the solution, and the x component now is sine. And that gives us a particle in a one-dimensional box, right, the quantum well. We do the same thing for the quantum wire, and now we have 2 dimensions where we have standing waves and one is a traveling wave. In the quantum dot situation, we have all 3 dimensions as standing waves. And that leads to discrete states for the density of states, and the density of states for those 4 different cases are shown down here. We're familiar, of course, with 3-dimensional objects having an e to the 1/2 power dependence. And for quantum dots, we basically have a series of delta functions, right, ideally. Your question? Okay. Okay, so this data table is taken from Gersten and Smith, which is a nice reference for kind of the basics of quantum physics on these dimensionally confined objects. So one of the most important results of quantum confinement is, of course, the dependence of the band gap on the size of the object. And I showed here data for cadmium selenide, showing a couple of interesting things. So we have data for 15 nanometer particles all the way down to 1.7 nanometer particles. And as we decrease the size of the quantum dot, of course we get a strong blue shift in the first exciton absorption feature, the onset of absorption. So we start from about 1.75 eV and we go all the way up to about 3 eV. That's kind of the energy range that we can span. I showed back here this density of states should be a series of delta functions. Well, that's of course in the absence of all kinds of disorder and thermal effects. And so what you actually find is that, take for example this spectrum here, you have a series of Gaussians that are overlaid across one another. And so you get kind of broad Gaussian-like features instead of discrete transitions. That's because of the size distribution of the particles not being ideal, because of thermal effects, and because of other effects. The band gap goes more blue, and so does the wavelength of emission. And so this is actually photoluminescence coming from quantum dots, cadmium selenide, that have been illuminated with the black light in this case. And so the absorption and the emission should track. So this is a nice picture of about a 5 nanometer cadmium selenide dot showing the absorption in blue, and the emission, which is nice, tightly focused, very strong Gaussian, that usually has quite a large Stokes shift for quantum dots in general. So you can get very large PL quantum yields from these materials. 50%, 80% is not impossible to achieve. And because of the large Stokes shift, and it's usually a little larger than shown in this particular set of spectra, they're useful for things like luminescent solar concentrators and other kinds of applications for solar, where you want to absorb and then you want to emit but not reabsorb the light. Okay, so cadmium selenide is of course the most heavily studied of the quantum dots, but it's not too useful for solar applications, not directly, because its band gap starts in bulk at 1.75 approximately, and then just goes blue from there. So what we need to do is to use a material that's actually more relevant for solar, and one class of materials that is more relevant are the lead salts. So these are compounds that start off with band gaps that are around 0.2 or 0.3 electron volts. And that because they have very large Bohr exciton radii, we can very easily quantum confine them at fairly moderate sizes. And so we can increase their band gap up from the IR and all the way, in this case, for lead selenide, up to about 1.5 electron volts or so. And so the place that we want to be for solar applications, especially when we're talking about multiple exciton generation, is between about 0.6 and 1 or so, 0.6 to 1.1, for example. And so lead selenide, lead sulfide, lead telluride cover this window very nicely. And that's one of the reasons that these materials are so heavily studied, as opposed to others that might not, for example, have lead in them or have other kinds of drawbacks. Okay, so why even study quantum dot photovoltaics? Why QDPV? Well, I think there are really two main reasons that QDPV is interesting. The first is the potential for enhanced efficiency, and the second is the potential for very low cost. And those are really the two things we care about in PV. We want high efficiency at essentially zero cost would be best. So let's look at enhanced efficiency. The reasons that these materials might be good for even ultra-high device efficiencies is that they can access some new kinds of physics. For example, multiple exciton generation is something that Matt Beard talked about and Arnozek talked about. And this is a phenomenon whereby, of course, if you absorb a high-energy photon, you can, with some probability or some efficiency, produce multiple electron hole pairs across the gap instead of just one. And so we save some of the thermalization losses that are typical in semiconductors. There are a couple of reasons why in quantum dots this process is favored over bulk materials. Matt talked a little bit about that. But the bottom line is that if you can harness this effect, not only at the femtosecond scale, but also over large distances so you can collect the carriers from the devices, you can in principle get up to about 44% overall power conversion efficiency, and that's at one sun. At concentrated light, it's even higher. Right? So you get an additional benefit under concentration. Now, not only MEG is interesting, but also hot carrier effects come into play with quantum dots. And quantum dots offer a way, perhaps, to make multi-junction cells that are above the Shockley quasar limit. Using a single material, by just changing the band gap, we can, for example, make a triple junction solar cell. So it might be a way to get that sort of efficiency enhancement using a fairly low-cost approach. And so that takes us then to point two. Of course, these materials are solution-made at fairly low temperatures. And that offers the possibility of doing low-cost roll-to-roll type production for large area solar cells, for large area photovoltaics. And if you can print solar cells like you print newspaper, that might offer certain economic advantages. It's not guaranteed to, but it has the potential to. And so these are the two main motivations for research in this area, from a practical perspective anyway. So if you think about how you might take quantum dots and implement them, how you might stick them in devices, there are a couple of different device classes that really pop up immediately, in my mind anyway. And I just put three of them here. So you could consider, for example, using quantum dots to sensitize a Gretzel type device. So making a quantum dot sensitized solar cell, where we take, let's say, lead or cadmium quantum dot and decorate them on a titanium or some other sort of high area oxide nanocrystalline film. And you have your electrolyte and your counter-electrode, just in the normal, as in the normal devices. So this is an area of some ongoing research, and I think that there's been a couple of breakthroughs recently. Some challenges here are actually trying to infiltrate these particles into the matrices, or the interstitial spaces between the nanocrystals, and also to get good charge transfer from the quantum dot into the titanium particle. That's another challenge. And a third thing is corrosion resistance. So typically people use iodide triiodide electrolyte, and that tends to etch a lot of 4,6 and 2,6 compounds. But recently there's been some breakthroughs in the dye-sensitized solar cell field, and so people are now using non-corrosive electrolytes, for example. So I think there are a lot of new opportunities for using quantum dots in these devices now, whereas before it was difficult to get high efficiency devices because the materials combinations did not agree with one another. A second way to go is to make a bulk heterojunction using quantum dots as the acceptors for, say, a conducting polymer material. So P3HT quantum dot solar cells or something like this. This is also an area of ongoing research. I think NREL has some very good results in the last year on this, maybe 4 or 5% devices, I don't remember exactly. And so In this case, you could, for example, benefit by using the quantum dot's ability to absorb light much more strongly than the PCBM and enhance the overall light conversion efficiency of this kind of heterojunction device. A third approach is to use what are called quantum dot solids. And quantum dot solids, again, are conductive films of pure quantum dots. In this kind of layout here, you could imagine making a quantum dot solid and basically putting it in an environment in which you have a PIN kind of structure, a PN junction type structure, or a Schottky kind of solar cell. And this is the kind of device that we ended up focusing on when I was a postdoc at NREL, and have since continued working on these kinds of devices. It was really for a number of reasons. When I was at NREL, we were trying to make a device platform that would show MEG photocurrent, something that would produce a lot of photocurrent. And this kind of device popped out at us because of its simplicity in principle. It's all solid state and it's all inorganic, and so that had advantages for us. This is a device that has the highest quantum dot loading compared to these other two. And it also has the fewest heterojunctions. So we don't have junctions between liquids and semiconductors. We don't have junctions between organics and inorganics in this kind of device. And so this lent itself to much more kind of direct interpretation and comparison with existing semiconductor devices, silicon devices, and compound semiconductor devices. And so that's what I'm going to focus on for the rest of the talk, are these kinds of quantum dot solids. So the idea is pretty simple. So we want to make, by some mechanism, by some method, a conductive quantum dot material, and we're going to focus for all of this talk on the lead compounds. And then sandwich this thin film in an electrically asymmetric environment that allows for charge collection, charge separation, and charge collection to be achieved. So in this particular case, we show an example here where I've got a lead selenide film on ITO on glass. So that's a metallic ohmic contact there. And then this back contact we make with calcium aluminum. And the back contact in this case is a Schottky contact. And so there's an electric field at this back interface that allows for charge separation and collection. If you take an SEM of what this film looks like, it looks something like this, and hopefully you can see it. It's basically a random close-packed structure of quantum dots. So this is what we would call a quantum dot glass, or a quantum dot amorphous quantum dot solid. And a TEM, of course, reveals that these particles are on the order of 5 nanometers and they're highly crystalline. The trick to making these kinds of devices is to be very gentle. So what we want to do is we want to induce a conductive film between these quantum dots without really perturbing their essential properties. We want to retain their band gap, which is the way that we actually get a device in the region where it can have a high efficiency. And we want to retain its ability to produce multiple carriers. Right? So the MEG efficiency we want in principle to retain or to actually improve. And so that means we can't do things like sintering, we can't do things like harsh chemical treatments that do lots of etching damage to the structures. We need to be gentle with them. Okay, when we think about what the requirements are for a quantum dot solid to be the absorber layer in the device, and remember that it's not just the absorber layer, but it's also the charge transport layer. We're going to have it putting on all hats essentially in the device, just like a silicon layer would do. We have basically 5 requirements that we need to work through. The first is, of course, that it needs to absorb light, right? And it needs to absorb all the sunlight if we can. So what that means is that we have to have a film that's thick enough to be able to do that. And with lead selenide, lead sulfide quantum dots, we're talking on the order of 1 micron film thickness is what we're looking for. That's enough with a double pass to absorb almost all the light above the absorption threshold. The second thing is the film has to be conductive. We have to get the carriers out. And this is where a lot of science and art and magic comes into play. So electronic coupling between the quantum dots can come in various forms. Most typically, it's some form of tunneling. Usually phonon-assisted tunneling is the active charge transport mechanism in most of these films. But there's also the possibility, if we can control disorder within the film, to produce mini-bands between the quantum dots and allow for then much higher mobilities, much better charge transport properties. And so this is one of the ongoing struggles in the field right now, is to move from tunneling to mini-band conduction. The third thing that we need a charge separating mechanism, so that means we need a built-in field or we need a donor-acceptor junction. This is one example of how we might implement a built-in field for one of these materials. where we have an NIP structure, where the quantum dots are in the I layer. So in this particular cell, you would have then electric field drop all the way across the quantum dot film, and that allows you then to collect charges by drift rather than by diffusive transport. And that in principle should give us a higher efficiency, definitely better collection. And so this is the kind of device that's used for low mobility materials, low diffusion link materials like amorphous silicon. Fourth, in order to get the carriers out, if we don't implement something like this, we need to have a large minority carrier diffusion length. And the diffusion length, as probably many of you know, LD, is the square root of the mobility multiplied by the lifetime of the minority carrier multiplied by the thermal voltage. Thermal voltage is 26 millivolts at room temperature. So when we think about increasing the diffusion length, that breaks down into being concerned about mobility, being concerned about lifetime. And in quantum dot solids, mobility turns into worrying about electronic coupling between the nanocrystals, between the quantum dots, charging effects, and also order, or really more specifically disorder. And then lifetime considerations. Lifetime basically comes down to recombination effects, and we're talking about Auger surface effects because the very, very large surface area within these materials. You can consider the surface to volume ratio to be very large. And also junction recombination at any of the interfaces, the active interfaces between the quantum dots and metals or the quantum dots and semiconductor layers. And then finally, we need long-term stability in order to have any sort of practical technology. Okay, so from here, let's talk a little bit about quantum dot synthesis. The synthesis, maybe most of you are familiar with. It looks something like this. Let me first talk about the goals of the synthesis. What we want to achieve with quantum dot syntheses are the following things. Monodispersity is one of the most important criteria. So we want monodisperse crystals. And that's so that we can actually make good structure property correlations, especially in the interpretation of the device physics. We need to have monodispersed samples. We would also like to be able to control size, so we can span from 2 nanometers up to 12 nanometers or something like that. Shape control would be nice. Doping is an area that's basically a failure right now for most of the quantum dot field. It's very difficult to dope controllably by the normal kinds of mechanisms. So what we rely on is actually doping by surface mechanisms, which I'll get to later. Surface passivation is important for this as-synthesized materials, and we want colloidal stability. And so this is what a typical synthesis looks like. It's a 3-neck round-bottom flask. We've got some precursors in here and some surfactants in here at maybe a couple hundred degrees. We've got this attached to a Schlenk line so that we can actually either purge it with argon or evacuate it. This is a thermometer. And here's where we would inject our active precursors, so the cadmium precursor and our selenium precursor, for example. What we get out of all the quantum dot syntheses is because of the fact that we put in long-chain surfactants, we get a material that is basically a two-component material. There's a crystalline inorganic core, which is the quantum dot, the central part of the quantum dot, and then there's an oily organic ligand shell on the surface of the dot. And this is one object, right? These are not separable features of this kind of object. So the way that normal quantum dot syntheses are sort of understood is using the Lemaire classical model of nucleation and growth. This is kind of the dominant model in the field, even though it's probably not right in many cases. It's still kind of the most an intuitive model. So what the Lemaire model of nucleation and growth basically tells us is that to get monodispersed colloids, what we want to do is have a nucleation burst in time, very short nucleation burst of dots, in our case, followed by, at later time, a growth phase. And that allows us to get monodispersed material. And so this is the classical graph showing concentration, solute concentration, or monomer concentration versus time. The idea is that you boost the concentration above the solubility limit, so you're in supersaturation here. There's some critical supersaturation limit where you actually get nucleation to start. The concentration goes up a little bit more, peaks, and then very quickly goes down. And so only in this region right here are we actually getting nucleation of our quantum dots. After that, the concentration falls below the nucleation threshold, no more nucleation, and then we just have growth of the existing cores. And this growth is usually by diffusion, so you have crystal growth regime kind of in here. And then if you keep on growing for large periods of time, then you run into some things that you usually want to avoid. Things like Ostwald ripening and aggregation of the quantum dots. So Oswald ripening happens at longer times, where you have the smaller dots giving up their mass to the larger dots, and the size distribution gets worse, and the sample coarsens. And aggregation, of course, is when you actually have clustering of these dots, and they get big enough that they fall out of solution. So those things are to be avoided. But this is the general understanding about how quantum dot syntheses work, even though, like I said, in many cases it's not probably that correct. Okay, so how do we do this in reality? We use something called the hot injection method, and I'll show just a demonstration of the synthesis for lead selenide quantum dots. So for example, we would take lead oleate, so OA as oleic acid, so we have lead oleate, and then we have trioctylphosphine selenide here as the selenium source in a hydrocarbon solvent at about 180 degrees C, and we generate in that balanced chemical reaction lead selenide. Okay? So here's what the temperature versus time profile would look like for the actual experiment. We would have our solution containing only one of the precursors at some high temperature that's been stabilized. At this point here, we inject, let's say, our selenium precursor into our lead, and this material is a little cooler, so immediately the temperature starts falling. The nucleation happens in a short burst in time and in temperature in kind of this indicated region. And then once the temperature gets down here, the nucleation window is, you're out of the nucleation window. And only growth happens. So growth happens from as the solution cools, as the heating source starts to heat the solution back up a little bit. This is your growth window. And then finally at the end, you do various things to quench the growth as quickly as possible to try to hold on to the monodispersity of your sample. What can be achieved is basically about 5% polydispersity in samples. And what that equates to is essentially atomic roughness. So 5% on a 5 nanometer dot, you're talking about less than a unit cell, so we've got atomic roughness control. But that is not enough, it turns out, to deal with some of the disorder issues that we'll talk about tomorrow morning. Okay, so inherited from these syntheses are the native ligands. So I call these ligands native because they come with the dots as they're born. They tend to be long-chain hydrocarbons, so oleic acid is very popular for the lead salts. But there's also other molecules like topo, trioctylphosphine oxide. This is more typical with the cadmium salts. And then DDT, so this is not Rachel Carson's DDT, this is dodecane thiol. Right? So you can have thiols, you can have amines, various long-chain phosphonic acids, and so forth. So the functions of these native ligands are several. So the first thing is these native ligands basically control the size and the shape of the quantum dots during their synthesis. And so these are what allow you to achieve monodispersed particles. They prevent aggregation in solution. They also have an electronic effect, so by sticking onto the surface, they can passivate dangling bonds and other sorts of imperfections on the surface. And that usually is what's responsible for the very strong PL that can be achieved from these kinds of materials. They may also dope the structures, although these molecules here are too long chain to really tell by DC measurements because they're so insulating whether they've done any doping at all, but it's quite likely that these head groups are actually doping the structure. And another important thing is that they isolate the quantum dot from its environment, so they give it some measure of chemical stability against oxidation and other problems. The other issue, though, is that because they isolate the quantum dot, because they're insulating, they make insulating films. And so it gives rise to something called the ligand problem. And so to get away from the ligand problem or to work around it, we have to find ways to get rid of that original native ligand and replace it with something that's much shorter or more conductive so that we can make conductive films. So typically we have oleate capped lead selenide. The way that we actually make films is by one of three main approaches. We take a solution of quantum dots, we do spin coating or drop casting or dip coating. And what we get originally is a film, maybe hundreds of nanometers thick. But these long chain oleates are sufficiently long to prevent the quantum dots from moving very close together. So the distance, the edge-to-edge distance is on the order of 2 nanometers or so. That means that the wave functions that are within each quantum dot have very little overlap, and so we have an insulator. And so to make a conductive film from this standpoint, we need to exchange these long chain molecules with short chain molecules. And so to do this, things like thiols, short chain thiols, or amines, or increasingly inorganic ligands are being used for this purpose. By exchanging with something smaller, you cause the quantum dots to nestle up together, so you can decrease the interdot distance by quite a lot, down to maybe a couple of angstroms. That allows good wave function overlap, and then you generate a highly coupled quantum dot film, and it's conductive. So some of the ligands that are used in this particular process are shown here. So EDT is ethane dithiol. That is probably the most used ligand for lead compounds. Hydrazine is one of the first, so hydrazine is just N2H4. BDT, benzene dithiol, is a nice one where you have an aromatic ring here that can actually participate, perhaps, in transport. And increasingly, like I mentioned, inorganic ligands are being used. So sodium sulfide, for example, is one of the most interesting at this point. Right? Something that's very, very small and also completely, or almost completely, environmentally stable. And so you can get the quantum dots very close together and improve the stability of the material. So let me just show you a couple of things, how these ligand exchanges actually work. So here's a ligand exchange with ethane dithiol. In this case, we're going to look at a spin cast film. So we spin cast the film onto a surface. We image it first, and we use FTIR as a very nice technique to look at, to quantify ligand exchange in these materials. So just as made, just spin cast before ligand exchange, it looks something like this. It's about 400 nanometers thick. And in FTIR, you can see very, very large CH stretch peaks, right, around 3,000 wave numbers. After immersing the sample then in a solution of EDT for a few minutes, just 3 minutes in this case, we have this kind of micromorphology where we have basically lots of cracks in the film. This is because of volume contraction. Right? So we're going from an 18 carbon chain down to a 2 carbon chain. That's causing about a 40% decrease in volume, and so it cracks like mud. You get this sort of morphology. FTIR shows that you basically quantitatively exchanged the material, so almost all of the oleate is gone. Right? And this is, in general, what one is trying to achieve, is a nice clean exchange from one molecule to another. So because this spin coating method gives you cracked films, you have to find ways to get around that problem if you're going to make devices, either in-plane or through-plane devices. And so the obvious thing to do is just to spin coat again, and again, and again, and fill in those cracks and then re-exchange each layer. So sometimes for solar cells that are made by spin coating, you do about 10 layers thick, something like that. Another approach is an approach that we use more often, and that is a layer-by-layer dip coating strategy. And this was shown by Matt Beard briefly during his talk. This gets around all the cracking problems. It has lots of advantages. Its main disadvantage is that it's slow. The idea is pretty simple. You take a substrate, you dip it into a solution of your dots in, say, hexane, and you withdraw the substrate, and that leaves a monolayer of quantum dots on the surface of your material, the surface of your sample. You then dip that sample into a solution that contains EDT. That causes the ligand exchange process to go on. That insolubilizes the nanocrystals and causes them to move closer together. And that gives you a conductive monolayer, essentially. And you can just repeat that process over and over and over to build up a film. The nice thing about this approach is that you can make films that look something like this. They're very dense, so basically randomly close packed or approaching that. They're optically flat, so their roughness is on the order of 1 quantum dot, even over square inches. They're uniform, pinhole-free, which is important for solar cell construction. And because of the method that is used, every layer that comes in is treated, and so it kind of relaxes before the next layer comes in. You have a low-stress film and usually very good adhesion to the substrate. So this is on a piece of ITO. Okay, so what actually are the effects of these ligand treatments? So we can see the effects in basically any of the properties that we look at. Perhaps the most dramatic and important effect is on the electrical properties. And a very nice demonstration of that is taken from Talkin's paper in 2005, a science paper, where they used lead selenide dots and hydrazine as the ligand exchange. So just look at the middle here, middle graph B. This is conductance, even though I think the units are wrong, but it doesn't matter, versus time of immersion in hydrazine. The film at the beginning, before touching hydrazine, has conductance, let's say, of 10 to the minus 10. And then after a couple minutes, we're up to 10 to the 0. So we have a 10 to the 10th increase in conductivity for this film. Right? And that's a really massive, massive increase, much, much larger than what had been seen in the past. And so basically the first thing that happens, of course, is that by removing the long chain hydrocarbon and replacing it with something that's short, we get a much improved conductance of the film. You can see then the IV characteristics for the before situation here and after up here. Afterward, what we have is a very nice N-type transistor, field effect transistor. And these kinds of structures, as I'll show you later, can be used to study the electronic properties of these films. So that's the basic impact on the electronics. What about the structure? So a lot of different techniques can be employed to try to understand exactly what's happening to the structure, the microstructure, and kind of the macrostructure of the film. once these films see the ligand exchange. So one important technique that's used is small angle X-ray scattering. So this technique is basically normal Braddock scattering, except you're looking at very small 2 theta regions, or we're looking at very large D spacings. So these peaks here, these reflections, are not from the atomic D spacings, but actually from the superlattice D spacings between the quantum dots. And what you can see in this kind of before and after, so the oleate capped film has a certain peak that's at a fairly large or fairly small D spacing here, fairly large D spacing. And then after the treatment with hydrazine, we see an increase in 2 theta, which means a decrease in the D spacing. That's direct evidence that we're actually causing the quantum dots to move closer together and kind of nestle up toward one another a little bit. Again, this is done on a superlattice film. TEM is also a way to give kind of direct information about what's going on, but it's usually limited to 2-dimensional subjects. So you can't look so much at thick films with the TEM, but you can see here's oleate with a nicely separated hexagon. You're aniline treated, where the quantum dots are a little closer together, and then EDA treated, ethylene diamine treated, and the quantum dots are basically touching after that. So TEM is useful. And then finally, optical spectroscopy can also be very useful, basically by monitoring and following the position of the first exciton, not only in terms of its location, but also in terms of its width. So what I showed here are 3 different spectra. This is taken of dots that are coated in oleate before film formation. And then the red is after EDT, and the blue is after a treatment by sodium sulfide, so this very, very small inorganic ligand. And what we see here is we see a redshift just going from the asmade to the EDT-treated material. This redshift here has several different origins, but one of them is the increased coupling between the quantum dots. The other origins include things like dielectric constant change. The dielectric constant increases when we cause the dots to move closer together. The other thing that can happen is that you can see, for example, in the blue curve, the sodium sulfide treated material has a significantly broader peak shape in this case. So this is an example where perhaps we have not only increased the coupling and increased the dielectric constant of the material, but we've also increased the size distribution of the material. And so if you increase the size distribution, you expect a broadening in the first exciton peak. But the bottom line is that ligand exchange we can, by many different methods, correlate to a smaller interdot spacing. So even kind of zooming farther in, modeling is often useful to understanding exactly what the structure of the region between 2 quantum dots might look like. And so I just showed here a quick DFT calculation, where what we've done here is taken 2 slabs of lead selenide that are 1-1-1 oriented, and stuck in between them either EDT molecules or sulfide ions, and then allowed the simulation to relax the structure. And what we're interested in identifying here are 2 things. First of all, what the general geometry looks like, and then second of all, what the interdot spacing was. And so this number and that number are the interdot spacings, as defined as the spacing between this layer of lead and that layer of lead, the first monolayer of lead on each dot. And so what we see is that EDT can draw, in an ideal situation where we have planar quantum dot slabs, can draw the quantum dots together to be about 6.4 angstroms separated. The sulfide, though, is much smaller, and so it can draw the quantum dots together by about 3.8 angstroms or so. The other interesting thing in this particular simulation is that we see that with sulfide, by bringing the dots very, very close together, we also open up the opportunity for direct bonding between the lead and selenium atoms between the individual dots. And this is something that people are very worried about and interested in, using these very, very small ligands, that we may actually be doing things like necking particles together, causing some very limited fusion of the quantum dots, which will improve charge transport to some degree, but it also will increase the disorder within the material. And we'll talk about that in detail tomorrow. So this is a hint, perhaps, that we're seeing quantum dot necking in our simulations. Okay, zooming way out now, let's look at kind of the final general impact the ligand exchange has. So this is, again, an SEM, another SEM of films that are treated in different ways. So this particular film is just spin cast, and this is before any ligand exchange at all. And what you can see in this particular case is that we have a nice superlattice film. Right? These are oleate-capped quantum dots. And I like this image a lot because if you didn't know it was quantum dots, it looks very much like an STM of an atomic solid. You can see all the features of an atomic solid here. You can see lattice, terraces, you can see step edges, some very nice ones. You can see defects like theirs where a single quantum dot is missing from this particular terrace, and so forth. But the bottom line is that with using the oleate cap material, we can make superlattices that are quite nice. But they are also electrically insulated. Right? They will not conduct current because of the presence of the oleate. Anytime we do a ligand exchange, no matter how we do it so far, we end up destroying the superlattice order of that original film and producing something that's conductive, yes, but also amorphous or glass-like. So we make conductive glassy films after ligand exchange. And it doesn't matter whether we do spin cast and then ligand exchange in situ, or whether we do dip coating, which is how this particular film is made, or whether we do ligand exchange in solution and then try to cast the dots into a film that's a superlattice. So far, people have not been very successful in making conductive quantum dot superlattices. The reason that we care is because a superlattice that was conductive, like with this kind of nice order to it, might have improved charge transport characteristics. It might be good for solar cell use. Okay, so let's talk finally about charge transport in ideal quantum dot superlattices. Let's say that we were able to make conductive quantum dot superlattices. What would we expect for their charge transport properties? Well, basically, quantum dot solids are a new and I think quite versatile type of granular conducting material. And we can understand them as basically an array of conductive islands that are given by the inorganic cores that are separated from one another by insulating tunnel barriers. The tunnel barriers have a certain size, that is, they have a certain height and they have a certain width. The width is set by, in this case, the length of the oleate molecules and how they interdigitate between the quantum dots. And the height of this barrier is set by the electronic properties of that material. So what we can do is we can actually tune coupling within this kind of assembly in one of two different ways. We can increase the coupling, the electronic coupling between quantum dots by adjusting the distance between the dots, say by removing the long chains and adding short chain ligands in their place. And in an ideal situation, you retain the perfect order of the array. What you would have then is a barrier width that's much smaller. And that's going to give you much better coupling, that's going to give you higher mobilities. Alternatively, what you could do, instead of worrying about the distance between the dots, you can worry about the stuff that's between the dots, and the identity and the electronic properties of that stuff. And so you could, for example, replace the oleate with an inorganic matrix. So we call this matrix engineering. And the idea would be that if you used a matrix that has a smaller band gap or a smaller effective mass, then you would lower the tunnel barrier height. And so the distance would be, the width would be the same, but the height would be lower. And that, of course, will also increase the coupling within the film and give you a conductive material. And so there are lots of efforts in the field right now to try to combine these two strategies in order to tune coupling and tune the electronic properties of the materials. Now, in the ideal case, and by ideal I mean that there's absolutely no disorder within the film, that all of the quantum dots are exactly the same, that the distances between them are all precisely identical, that there are no surface traps or other kinds of recombination centers, etc. in the material, and that there's no electron-electron correlations that could lead to things like Coulomb blockades or Mott insulators. When we have that sort of situation, then what we're going to get in terms of charge transport properties is going to be coherent resonant tunneling. Coherent meaning we have very long extended states, kind of block-like transport within the material. Resonant because all of the energy levels of all the quantum dots are exactly the same, so we have resonant tunneling. So in this limit of ideal superlattices, people have actually modeled what to expect in terms of the numbers, and a little bit more about the intuitive aspects of the physics when we have these kinds of quantum dot solids. There have been a couple of different modeling efforts, starting by Blandin in 2001. I'm going to talk here about some results from Martin Green's group in 2006. So what they've done is basically realized, of course, that quantum dots are artificial atoms, and that if you get them close enough together in a regular array, the confined levels between or within each quantum dot will overlap, and you're going to make bands. You're going to make mini bands in this case, not normal bands with normal bandwidths of an electron volt or 2, but mini bands with a bandwidth of 0.1 electron volts. So here's the kind of model that they did. They were particularly interested in silicon in different matrices. These are silicon dots that are cubes, 2 nanometers on the side, and there's a separation of some controllable amount. They used effective mass envelope calculations to determine the band structure of these particular solids. So basically solving the Schrödinger's equation, but not for a single electron, but rather for the envelope function. And so this is what they see here. So this is the band structure, for example, for 2 nanometer silicon cubes with 1 nanometer spacing in a silicon carbide matrix. So silicon carbide is the insulator in this case. And if you squint, you can see that we have bandwidths here on the order of about 0.1 electron volt. And kind of all the things that you would expect to happen. So here's a plot of the energy versus the interdot distance. As we bring the quantum dots closer together, what we see is that we get increased bandwidth for these particular 2 states. It doesn't matter which states they are. But as we draw the quantum dots closer together, the bands get broader and broader and broader, as we would expect from atomic physics. Just thinking about tight binding calculations or something. The other thing is that here's a plot of energy versus the barrier height. Right? So what I'm showing here is the interdot distance, which is the first thing that I described. Showing here is lowering the insulator barrier height. If we do that, if we bring the barrier height from 3 eV down to 0.5 eV, we see not only a reduction in the energy of the system, but we also see opening up of bands for both of those particular states. They're not as wide as these. The dominant effect is really the interdot distance and not the barrier height, at least for these particular, the numbers chosen here. But it gives you an intuitive sense for what to expect in the ideal situation. And so what you can do is you can take the band structure and you can actually calculate using a couple of approximations or estimates for the lifetime especially. The mobility of the electrons in this case is what they look at. And so the mobility, of course, is just the fundamental charge multiplied by the scattering time divided by the effective mass. And this effective mass is going to be the effective mass of the superlattice. And we can pull the effective mass of the superlattice directly out of the band structure. It's just inversely proportional to the curvature of the band, at whatever position we're talking about. And what they found is that, this is a plot of this, and I'll get to that in a second. What they found is that you can get mobilities in this particular simulation up to about 125. And that's with an assumption using tau of 30 femtoseconds. So that's the scattering time, the time between scattering events for electrons. And then this summarizes very nicely all of the different expectations for a perfect superlattice. So we have interdot distance along the x-axis, mobility along the y, and we've got 3 different situations, 3 different, basically, matrix materials. Silicon oxide, silicon nitride, silicon carbide. We see that as we decrease the barrier height and we decrease the interdot distance, we maximize the mobility. These mobilities, if we could achieve them, even say a quarter of them for the solids that we're talking about, would give us diffusion links that are long enough to really collect all the carriers, or at least collect all the light, and probably all the carriers from the devices. So this is something that is kind of motivating goal for our work in manipulating quantum dot solids. And it assumes, like I said, perfect everything. Right? Perfect quantum dot superlattice, no surface states, and also no scattering from phonons. How much time do I have left, John? Okay, good. So I'll just finish here. So what I'm going to talk about tomorrow is the reality of the situation. Okay, so we have charge transport in ideal quantum dot films look like this, but in reality we have the ideal versus the real, and the real looks something like that. Right? Something very ugly, where all the quantum dots are misshapen, different sizes, there's different distances between them, orientations are all off, etc., etc. So we will analyze the effects of all of this disorder and what it means for our potential for making high-efficiency quantum dot cells tomorrow morning.
All right, very nice. Any questions for Matt?
I have a question. You have told quantum dots are 0-dimensional, and when we are decreasing the size, there is a blue shift. So is there any size specification? What is the maximum size for the quantum dot and the minimum size?
You mean when you see quantum confinement effects? So there are, depending on how you divvy it up, there are basically 3 regions. There's the weak confinement region, well, there's the no confinement region, weak, and then strong confinement. And it's dictated by the Bohr exciton radius. So if your structure is, less than the Bohr exciton radius, smaller than the Bohr exciton radius, then you're considered to be strongly confined, and you should see pretty extreme effects. But also in weak confinement, you should see decently strong or decent confinement effects as well. So maybe I don't know if there's a hard cutoff, but it might be three or four times the bore radius. Yeah, something like that.
Thank you so much. I just had a quick question about, so you mentioned that when these dots get too close together, you have these bonding between the atoms.
Yeah.
How does that affect these mini bands that we're talking about? Or does it affect them?
It would, yeah. So what we're going to find tomorrow is that basically any disorder that's extreme like that, when you have two quantum dots together but not touching, they still behave as, let's say, 5 nanometer dots, but just tightly coupled. But when they start necking together and they're actually physical points of contact, then suddenly the exciton or the electron can delocalize over a much larger part of the structure. And the confinement energy is much, much lower in that case. And so if that kind of disorder is present in the system, then it can really wreak havoc on mini-band formation. But it depends. So you can still have them, but you have to have very strong coupling.
Thank you for your nice slide. My question is that this tunneling of carriers between these nanoparticles, is it the tunneling of free carrier or the whole exciton is transferred?
So when you have strong coupling, which is kind of what we're always shooting for quantum dot solar cells, what people are finding is that the yield of free carriers is very high. So sometimes unity. And so mostly what we think about is charge transport rather than exciton transport.
So is there any explanation why there is this charge separation during the tunneling?
So it depends on what we're talking about here. So a lot of the devices that we use to actually measure the properties of the materials are field effect transistors. And so we're actually just injecting single types of carriers into those. So at that point, in the dark, we don't have excitons per se. So we're looking at just charge transport. When you're looking at illuminated properties, it's different. So you're asking what causes the initial exciton to split,
Yes.
right?
Because right now, when we are talking about two nanoparticles or two quantum dots, we don't have a built-in field.
Sure. So that's a good question, and I don't think it's really well understood. There are a number of possibilities, right? So one is that you can have a superposition of excitonic states and charge transfer states, and you just leak out a bunch into the charge transfer states. You can also have electric fields that are just at the interfaces between dots that could be responsible for ripping excitons apart. You can have charge traps for one kind of charge and not the other. So the details we don't know yet, I'd say.
Thank you.
Or I don't know.
Yeah. So if you did a replacement to ligands with not a wide band gap semiconductor, but a narrow band gap semiconductor,
Yeah.
and then have the film that's kind of like not a quantum dot film,
Yeah.
like the inverse.
Yeah.
Has anyone looked at what sort of interesting properties that would have, and whether there's any interesting quantum confinement effects? Because the conductivity of that film would be excellent. You
Yeah.
still have quantum confinement effects.
Right. So yeah, you're talking about making basically a bulk heterojunction with inorganics, right? Because you want continuous matrix,
But on one of the materials.
right? And then the dots are still separated from one another, but that's material too. So those materials have not really yet been made. There are active efforts underway to do that. I'll talk about it tomorrow. So we're trying to use atomic layer deposition to achieve that kind of thing. But it's slow going. But you're right, it would be a very interesting material to look at. Sort of flip it on its head.
Any more questions? Well, let's thank Matt again.